What if one strange clue from the past suddenly fit into place today? Think about that for a second, because this story takes a surprising turn the moment a forgotten device shows up again. People who thought they already knew the full tale are now asking themselves questions who would not. Could this mysterious sphere be the same type Bob Lazar described decades ago, or is humanity staring at something far stranger? On March 2, 2025, people in Buga, Valle del Cauca, Colombia, recorded a round, shiny object moving across the sky. Clips taken showed a smooth, metal ball moving low over streets and fields. They appeared on social media platforms within hours. People rushed to see what had happened out of curiosity. Someone picked up a small metal sphere from a grassy area near the road. Reporters also reached the site within a flash of a second. Mexican journalist Jamie Mauson helped in spreading the news. He invited other reporters, technicians, and a few researchers to broadcast the incident. Technicians placed the sphere on a table and moved it using gloves. The crowd watched as they displayed X-ray images on screen. The images showed bright shapes inside the round shell. Presenters pointed to a small central object in those images and to several small round pieces around it. Later reports showed different numbers for those pieces. Some images showed 9 inner beads, while other images showed more, raising many questions. During the presentation, Dr. José Luis Velázquez shared a little about the images as engineer Rodolfo Garrido explained parts of this device. Researcher Carlos Muñoz described how the images were taken. They said the outer shell looked smooth with no visible seams. A short clip showed someone pouring water on the sphere that produced a pale vapor. Cameras recorded the small cloud. Reporters collected statements that said plants near the landing spot looked damaged. A few neighbors said they felt sick after touching or standing close to the device. Those health reports appeared in interviews, but no formal medical report was shown to the public at that time. Videos from the site showed the recovered sphere wrapped in cloth as it was being removed from that place. Those clips helped track the chain of events but did not replace lab records. A clear paper trail would list who took the item, who stored it, and when it moved to the laboratory. Different journalists quoted different weight and size descriptions from presenters at the event. Some said the object felt heavy for its size. Others said it felt light. The stage commentary used words such as core, shell, and beads to describe what appeared in the images. Despite being discussed at the site, the public still needed test results to verify those claims. Video clips and pictures taken that day pushed the story onto international news. People compared the images to old claims about secret projects and unusual power devices. They also posted side-by-side images and thoughts. Technicians warned about rushing to conclusions. The media attention brought more people to question the object, to record more images, and to ask who would test it next. Authorities secured the scene for a short time while videos kept circulating. Within a day, the device was already the topic of discussion everywhere. The reporting by Jamie Mauson drew media attention. Media coverage described the sighting, the recovery, and the first public images. Questions from reporters at the event helped enlighten people, leading to others asking questions about possible danger. Some asked how labs would test the object and what could happen afterwards. So far, the scene had film footage, a reporter, and members of the public as witnesses. This object, as strange as it is, made people ponder it. Do you have any idea of who handled the sphere after recovery, which labs would run the tests, and when the open test results will appear for the public to see? But what secrets lie within its mysterious core? Could this tiny sphere hold clues that defy explanation and challenge science itself? The images shown in that day's presentation raised many questions. The team on stage showed X-ray images and scans. They pointed at layers in the shell and talked about a small core inside the ball. Presenters also talked about many tiny round pieces around that core and the bright color coming from the device. Some steps had to be followed in the laboratory. First, laboratories record who handled the object and when. This record is a chain of custody. It shows the path the item took from the field to the laboratory. Without such a record, it is hard to trust the results, therefore raising the authenticity of the lab reports. Second, laboratories inspect the surface with a microscope, which tells if the item was cast, molded, or machined. Machined parts often have small marks from cutting tools. Cast parts have grain patterns that look different. These signs help technicians tell how something was crafted. Third, lab technicians run X-ray fluorescence tests. X-ray fluorescence is a quick test that shows which elements sit on the surface. Elements are basic building blocks of matter. This test does not destroy the object, as it gives a fast readout for metals such as iron, aluminium, titanium, nickel, and copper. If the object shows common metals, then that is a normal result. If the object shows rare mixtures, technicians will take more samples for deep tests. Fourth, laboratories may use mass spectrometry. Mass spectrometry reads tiny bits of matter to name exact atoms and isotopes. An isotope is a version of an element with a different number of neutrons. Some isotopes last a long time. Others break apart fast. Known heavy elements made in laboratories usually last only for a short time. If a test shows strange isotope ratios, that would be notable. It would require more testing by other researchers. Fifth, laboratories use electron microscopes to look at tiny structures. Electron microscopes show details that a light microscope cannot see. These machines can show crystal shapes and thin layers. They can also reveal coatings that hide marks. If layers exist, laboratories can slice a tiny piece and study the cross-section to see how the layers join. Sixth, laboratories may run gas tests if vapor was seen. Gas chromatography is a way to separate and name gases. It can say if the vapor was water, oil, a chemical, or something else. If a test shows toxic gas, laboratories alert health authorities. If the vapor is water vapor from heat, that gives a simpler explanation. I hope we are together up to this point. Do not get lost, ask questions if you have any. Seventh, laboratories measure radiation and fields. Radiation counters show if the object emits particles. Magnetometers measure magnetic fields. Small heat sensors can indicate tiny temperature changes. If an object emits energy that normal tools cannot explain, technicians add more sensors and repeat the work. Eighth, laboratories may weigh and measure density. Density is mass divided by volume. Knowing density helps match a material to known metals. For example, iron is heavy for its size. Aluminium is light. If a mass and volume do not match known metals, that is a reason to test more. Laboratories also may open the object if rules allow. Controlled disassembly happens under strict safety rules in a clean room with protective gear. Technicians label each part and test each part on its own. If the item has wiring, sensors, or familiar electronics, that will show quickly, and if no wiring appears, technicians look closer to see if some parts are bonded in other ways. At the scene, the images shown were not backed by full laboratory reports in the public records. Specialists shared with the crowd, but they did not publish raw data files that technicians use. Without raw files, outside teams cannot repeat the tests easily. Neutral research groups often push for open methods. Open methods mean laboratories publish methods, settings, dates, and raw data so others can check the work. That process helps the broader scientific community evaluate results. Without open methods, claims will never go mere talk. What would change the public view? First, open laboratory reports from a laboratory. Second, repeat tests done by more than one team that reach the same results. Third, a clear paper trail showing who handled the item and when. These steps move a claim from a stage show to a verifiable record. Many technicians use simple tests early on. For example, they may rub the surface, take pictures, and run a quick X-ray fluorescence scan at first moment. They also take small samples under supervision and store them in sealed containers labeled with the time and date. These samples become the basis for deeper research. If a sample shows regular metals and clear machining marks, the case becomes less strange. If tests show unusual isotope ratios or materials that do not match any known alloy, more researchers will join. The work then becomes a broader effort. Some researchers said they would accept samples under strict protocols. The public wants those teams to act and show the full test records so anyone can check them right away. Who will run those open tests and share every raw result with people around the world? Yet as the world waited for proof, cracks in the story began to emerge. Could these results really be trusted? Many scientists and researchers reacted to the news by asking for open tests before accepting such claims. Some experts said the images were interesting, but there was not enough proof. They pointed to gaps in the testing process shown on stage. One major issue was the paper trail that tracks who handled the object. Scientists want a clear record that shows who recovered the item, who stored it, and when it was moved to a laboratory. A sealed chain helps rule out tampering. That record was not shared on the day the news broke out. Another issue was the variation in the images themselves. One slide showed 9 small round pieces inside the shell. Later images showed a larger number. That change made many people ask for the raw scanner files and the original images. Raw files let other technicians check the same data. Skeptics offered simple explanations for what was seen on the screens. The object could be a piece of art. It could also be a machine component, such as a bearing or a sensor housing. Many industrial parts use inner balls for balance. A smooth outer shell can be produced by casting or molding. Those images alone cannot rule out these common causes. Scientists urged more testing by reliable laboratories. Research centers usually follow strict methods and publish full test records. Those records list which machines were used, the dates of testing, and the exact settings. They also share raw result files so other teams can review the numbers. That open method makes results easier to check and trust. Claims about health and soil also needed proof. Some people said crops near the spot looked damaged. Others said they felt unwell after coming into contact with it. Medical checks and soil tests can examine these reports. Doctors and environmental laboratories can test blood, air, and soil for chemicals or radiation. If tests show no unusual results, concern will ease, and if tests show odd results, more work will follow. The presenter, Jamie Mawson, has a long public history. He has promoted several unusual objects before. Some of those earlier objects were later questioned by outside researchers. That past led many scientists to tell people to wait for neutral lab work before concluding. Groups such as the Galileo Project were suggested as partners for open testing. The Galileo Project aims to study unusual objects using public methods. An open approach means full data release and repeated tests by different teams. Like, comment, and subscribe channel.